So it's pretty easy to see for our extended objects that are able to rotate about a single point, it's easy to imagine how an object that rotates has angular momentum. Sort of a more difficult question to sort of conceptualize the answer to is, does a particle that's moving in a straight line have angular momentum? So do particles themselves, if I come back to thinking about my object as just a point mass, can that point mass have angular momentum? And the answer here is yes, but the value of the angular momentum depends on where you put the pivot. So it can be that your particle has an angular momentum of 0 simply because of the choice of pivot where you're doing your calculation of the angular momentum from. So as an example, let's say I've got 3 different observers. So an observer at point A, an observer at point B, and an observer at point C. They're going to watch this car as it moves to the right at a constant speed. For which observers does the car have a non-zero angular momentum? The thing that we're going to see here is that the line that the linear momentum lies along is called the line of motion. It's basically nothing more than just saying since the linear momentum always points in the same direction as the velocity, the line of motion is the line that the velocity vector lies on. And in this case, what you notice is the observer standing at point B happens to be at a point that lies along the line of motion. So what we'll see is that the observer at point B, the angular momentum for the car as it moves to the right is 0. For the observers at A and C, that angular momentum is not 0. And one way to think about this is if you think about what each of these observers are doing. The observer at B simply watches the car move away. But the observers at A and C have to turn their heads to keep watching the car. Part of what that's indicating is if your head has to turn to watch, in this case the car, in general, a particle move, then that particle is going to have non-zero angular momentum from your location. So again, this is all about your choice of pivot point in terms of not just the magnitude but also the direction of the particle's angular momentum. The observers at A and C would see non-zero angular momentum for the car. So how do you calculate out the angular momentum for a particle? Like many of our rotational quantities are, it's defined by a cross product. And so again, capital L is the angular momentum, and that's equal to r, the position vector of the particle, the cross product of r with p, the linear momentum. And so again, if we think about some angle between those two vectors, so there's r, where my object is located, it's moving with some velocity in that direction. I can redraw those two vectors so I can see what that angle phi is between the position vector and the linear momentum vector, and then I can calculate out the magnitude of the angular momentum as magnitude of r times the magnitude of the linear momentum times the sine of the angle between those two vectors. And I know that the linear momentum is given by mass times the speed of the object. So this becomes mass times the object's speed times the length of that position vector times the sine of the angle between r and p. If we think about partnering sort of this length of this position vector and this sine term, what I recognize, of course, is that r sine phi happens to be this component of the position vector, which means it's the component of the position vector that's perpendicular to the object's linear momentum. So the only component of this position vector that matters in terms of thinking about the angular momentum of the particle is the component that's perpendicular to the particle's linear momentum. Another way to think about this is, of course, it's the component of the position vector that's perpendicular to the line of motion. So again, what r sine phi is doing is it's telling you about some perpendicular distance to the line of motion. And so what we can do is we can redefine how to calculate the magnitude of the angular momentum in terms of that perpendicular distance. So again, we've got m, mass of the object, v, the object's speeds, and now little l, we've defined to be the perpendicular distance from the pivot to the line of motion. So little l here plays exactly the same role that the moment arm or lever arm did in our torque calculation. It's a perpendicular distance. In this case, it's to the line of motion rather than to the line of action in our torque equation. So if we come back to think about our car and the three observers, well, of course, when the car moves, because observer B is sitting on the line of motion, there is no perpendicular distance from the line of motion to that pivot point, which means the angular momentum for an observer at point B is 0. A, on the other hand, there is a perpendicular distance from point A to the line of motion, so there will be some non-zero magnitude of the angular momentum. And again, in terms of thinking about our right-hand rule, because this is a cross product, the angular momentum, according to the observer at point A, points into the plane of the board here. For my observer at C, again, there's a perpendicular distance from C to the line of motion, so there will be some non-zero angular momentum in terms of its magnitude. And again, the right-hand rule tells me that the direction of the angular momentum for the observer at C will point out of the plane here. This is a bird's eye view, a top-down view of this car and the three observers. The angular momentum at point A will point down into the screen in the way we're looking. The angular momentum for the observer at point C will point up out of the screen, back towards us as we're looking down on the picture here.